So now we're going to look a little more at the kind of offerings that you would get in the high-performance computing world with respect to multicores. So David has already started to put up his videos about GPUs, and in some sense that's one kind of offering in that space. Intel's answer to the GPUs is what's called MIC, multiple integrated cores, and when they release the product, its first name is Xeon Phi. There are lots of code names here. Knight's Corner is the name of the chip that first was released, but Xeon Phi is how it's or MIC is typically how it's known out there. And what it is very similar to a GPU. It's a coprocessor. So in this generation, it's a coprocessor that you put on an I/O board, one or several of these. Even though I believe strongly that within foreseeable time, weeks, months, probably not years, I would expect that this kind of technology, these kind of chips would not sit on an I/O bus. They would sit on the QPI, the coherence protocol of Intel's processor, to be more out playing in this world instead of being put on the side on an I/O bus. So here it looks like a GPU, and that it's lots of cores. In this example, it says more than 50 cores, and it has lots of graphics DDR, GDDR memory technology, which is slower memory technology, but also has a much better bandwidth. So they're banking on lots of parallelism, lots of concurrency, where bandwidth is more important than latency. Looking at the architecture underneath the hood, this is a marketing picture from Intel. They have the cores right here. So the blue boxes here are the cores. And in this architecture, what they release now is more than 60 cores. It's like 60, 61, 62 in that order of, that's the number of cores. They have, all these cores are running an x86 instruction set. With an enhanced instruction set. So what they've done here is they've added a much wider vector instruction than the ones that you have used in the lab. So this is a 512-bit wide vector instruction, and then that can be executed. And they have their support for 4 threads running on each one of these cores. So, more than 60 cores, each one running 4 threads, 240 threads is what you need to keep this chip happy. Also, the way they schedule these threads, as I talked about in the SMT video, yes, these threads have a restriction on them that the same thread cannot put instructions into adjacent cycles after each other. So each thread can only put instructions every other cycle. So if you're only running one thread, you're going to lose half your performance. It has coherent caches. So it's these caches that sit here, the first level caches are coherent, and you share a second level cache. It's once more, it's a ring-based cache coherence protocol they implemented, fairly standard cache coherence protocol otherwise. So more than 30 megabytes of L2 cache. You have some special function units, you have some scatter and gather kind of instructions, but most of the rest of the chip is used to implement the memory controller, the many graphics DDR controllers. You can have up to 8 gigabytes of memory connected to one of these. An interesting thing is that it runs Linux. It runs all your favorite languages. So Intel has talked about the strategy where it just recompile and run. You boot Linux on this and just compile your stuff and run it. Well, it's probably not just as simple as that. It's more than a teraflop double precision compared with NVIDIA. They are behind in terms of peak performance, maybe a factor 2. They've been criticized compared with NVIDIA that, well, why do you implement this x86 instruction set? It's going to require so many transistors, so that's going to decrease how many cores you can put on a chip. Well, they claim that only 2% of the transistors is actually devoted to the x86 instruction set, and instead most of the transistors are devoted towards implementing this little RISC core that execute the instructions. I don't know how much that is true, but that's part of the marketing story. So here you have in a nutshell, looking at one of these core blown up. We have how the core itself works. So you have a scalar unit, you have a vector unit. The vector unit executes these very wide vector instructions, and this is probably where most of the work is being done in high performance computing. And this is not that different from NVIDIA's graphics, in that graphics processors are really good at executing this kind of vector instructions, SIMD, single instruction multiple data kind of instructions. So look at this, as a 16, a bundle of 16 of what's being called core in NVIDIA's implementation. That's probably corresponds roughly to one of these things. You have L1 instruction and data caches, 32 kilobytes each one of them, and then you have, for each slice like this, for each core, you have 512 kilobytes of L2 cache, and that is, as I said, has to be divided between the 4 different threads that can run here. So it's 128 kilobytes of L2 cache per thread running on this chip. So the tool stack, I'm not going to talk too much about this. The tool stack is they Intel port their existing x86 tools there. We have ported our performance tool to this chip as well. So it looks like a reasonable, from a productivity point of view. You don't have to introduce new language, use new tools and so on. You can just take your favorite tools and move on here. So that looks like a reasonable approach. So Intel says it's just a x86 Linux box. Use your favorite languages, just recompile and run. And they provide compilers and their own tuning tools and so on. It's been fairly impressive, fairly successful in the high performance computing market so far. So it's used in the #1 system in the world. It's a system from China, and it has, right now, it's about 18% of all the flops total on the top 500 list, very much thanks to that gorgeous machine. But there are lots of questions. Can we afford to spend more than 200 threads just to make a single chip happy? And that is the same question that should be asked in the GPU arena as well. How many applications do we have this much parallelism that we actually can afford to spend 200 threads to make a chip happy? In my book, threads, that's a hard currency. You should, every time you use up a thread, you should expect to get some return. Use twice the many of threads, you should expect to be fairly close to twice the performance. And certainly here we're spending lots of threads. The question is, are we getting twice the performance? How much more than just recompilation is needed? Certainly you will need lots of tuning. You did the SIMD lab, the vector instruction lab, recently yourself, and you saw how hard it is to use those kind of instructions if you have to do it by hand. And it's not trivial for a compiler to be able to make the transformation. Also, certainly in the current offering, Xeon Phi does not have the same performance as you would get from GPUs, but potentially better productivity with the languages and tools that's available. But the question is, what will the market say about this? And the jury is still out. Just looking finally at where this chip is globally in the market. These are numbers from top 500 list, which was released a couple of days ago for this year. The top 500 list is released twice per year. And what we see here in the top pie chart is to see of the total number of chips used to build the 500 most efficient, most powerful computers in the world. About 90% of those chips are not accelerated chips, GPUs or Xeon Phi. So that's one take-home message. And as you see here, comparing Xeon Phi is, which color is that? Xeon Phi is the green color. It's 2% of the chips compared with 3% of the chips for Kepler and 4% of Fermi. In terms of flops, they deliver it's 18% of the total flops on the top 500 list. So if you see of the total flops produced, it's only like 65% that are produced mostly by x86 out of order big beefy processors, and quite a large chunk, almost 35% of the performance is actually produced by these accelerators. If you see how it was exactly 1 year ago, you can see that the portion that of the flops that are being produced by graphics has increased quite a lot here. And if you compare the specifics here, so back then Xeon Phi was 3% of the flops produced. Now it's at 18%. So the color code changes between these two. And if you look at, for example, the Kepler was at, back here, the Kepler was at 11%, and now it's increased to 12%. So it's certainly both NVIDIA and Intel's offering is increasing here when you look at the pie chart for what portion of the supercomputing power they produce.